Wait, what are our things?
I don't know, I'm filming right now.
Uh,
This will be in the video,
Hi, welcome to the cooking channel. Today we're going to be making hot dogs. So first, you're going to want to fire up the grill. Alright. So then you're going to want to get small natural beef franks. Oh. So these babies right here. Toss them on the grill. Then you'll just let them sit for about 5 minutes or so, and then we'll check on them in 5 minutes. Alright, so it's been 5 minutes, let's check on our hot dogs. Oh, looks like we got a whiteboard. So, here, let's just go ahead and find the relationship between tangent F and F double prime.
Hello! Today we're going to be learning about how to find the tangent line of a function using the derivative. Our problem is, given f of x is equal to x cubed plus 7x plus 2, we're supposed to find the tangent line of this function at the point x equals 2. So first, we start by taking the derivative of the function. That would be 3x squared plus 7. Then we would plug in our value x equals 2 into the derivative to find the slope of our tangent line. F of the derivative of f of 2 would be 3 times 2 squared plus 7, otherwise known as 19. And then we would also plug in our x equals 2 into the original function to find the y value of our point. This would be 2 cubed plus 7 times 2 plus 2. 24. Then we have all the values we need, our slope, our x value, our y value. Using point slope form, we can now form a basic equation. Y minus 24 is equal to our slope, 19, x minus 2. We can go even further and putting it into y equals mx plus b form. Y equals 19x minus 14. This would be the tangent line for this equation at the point x equals 2.
Go.
Wait, did you start already? Hello. Today we will be talking about the IVT, otherwise known as the intermediate value theorem. I have a ball, and I will be moving the ball from f of A to f of B. The motion of the ball is represented on this graph as a position time graph. When I roll the ball, it starts at f of A, a time value, and ends at f of B, a time value, and crosses a position point W. The ball must cross this point W at some point in time, which is equal to C. Therefore, as the ball's motion is continuous and is represented by this graph f of x on the interval from A to B, there is a y value represented by W, which represents the position of the ball that is between f of A and f of B. Therefore, there must be at least one value, C, of time where the ball crosses this position value within the interval.
Alright, so today we'll be discussing the MVT. And the MVT states that if f of x is continuous on the interval a to b and is differentiable on the interval a to b, then there's at least one number c on that interval a to b, so that f prime of c is equal to f of b minus f of a over b minus a. And then there's a graph right here that demonstrates that. So these kind of problems are helpful to find the average rate of change, which is essentially this statement here. That gives the average rate of change, and then the MAT states that there's at least one value, one x value at which that there's at least one x value on the interval where the derivative will be the average rate of change over that interval. Again, that's demonstrated by this graph here. And these kind of problems come in handy when trying to find if a person went a certain speed or not over an interval. That's been the main use of it so far on the AP. So yeah. Yeah, go.
Oh hey, I didn't see either. Well, it looks like Puya's gone, so I'm going to be taking over from here. So as you can see, we have three graphs here, which represent f, f prime, and f double prime. So let's say that the graph of f represents the position. As we can see, it increases position gradually, crosses the x-axis, and then begins to slow down until it reaches a point at which the tangent line at this point is has a slope of 0. So if we take the derivative of this position function, we get the velocity. And as we can see here, the velocity starts out positive, but constantly begins to slow and slope until it hits the same point at which the graph of f crosses the x-axis. At that point, the velocity begins to slow down and have a more negative slope as we reach the end of the graph. As we move on to f double prime, we now get the acceleration of the position graph. And the acceleration is just a regular negative slope line, which represents that it had a constant negative acceleration throughout the duration of the graph. This negative acceleration is marked by the fact that this is constantly decreasing and getting more negative, has a more negative slope as it reaches the end of the interval. Therefore, this is constantly decreasing in rate as far as the position. So you have f, position, f prime, velocity, and f double prime, acceleration. In the graph of f prime, these 2 points here represent critical points. Critical points are points at which the graph of f changes, has a slope of 0. Edit this out. And the relative extrema of a function can be noted by the critical points as noted by f prime. As you can see here, the critical points of this function are 0 and 0. This point here. Therefore, we can either say that these points either represent maximums or minimums of the function. We can tell because if the graph of f prime is passing from negative to positive, that would be a minimum of the function. And if the graph is passing from positive to negative, we have a maximum of the function.
Where does that take?
The concavity of the function can be drawn out by looking at the graph of f double prime. As you can see here, when the graph passes through the x-axis at this point, we call this point a point of inflection, at which we can determine the concavity of the function using the points of inflection determined by f double prime.
Positive f double prime means positive.
Positive.
Concave up.
A positive graph represents that the graph would be concave up. The function f would be concave up. A negative f double prime would represent a f function which has a concave down function. These three graphs over here represent the f prime and f double prime of functions such as sine, for example. This would be a graph of sine. The derivative of sine is cosine, and you have a graph of cosine, and this displays the same kind of traits and patterns that were mentioned in these three graphs. F double prime would be the derivative of f prime, so the derivative of cosine is negative sine, the negative sine graph, which would also represent the same characteristics of these three graphs. The same trends apply.